Okay, thank you very much. Yes, I'm going to be talking about how we can use passive seismic sensors to record turbidity current events in the same location that Pete's just introduced, the Congo Submarine Canyon offshore West Africa. So the rationale for trying to use these instruments, Pete's just introduced it really well. We can directly monitor turbidity currents, but it's not without risk, particularly to instruments which we need to have anchored within the flow path, such as ADCPs. Passive ocean bottom seismograph sensors can be located outside the flow path, so they offer a new opportunity to remotely sense turbidity currents at high resolution. Ocean bottom seismograph sensors contain geophones, and these record ground vibrations generated by seismic waves propagating through the seabed, which can be generated by geomorphic processes such as turbidity currents. You may also be familiar with this equipment to measure earthquakes. Very briefly on the study area, because it's already been really well introduced, we deployed ocean bottom seismometers in the Congo Submarine Canyon and Channel in 2 different locations. Sorry, I've just lost my presentation. Oh, there we go, it's back now. Yes, so we deployed OBS instruments in the Upper Canyon and also so the OBS instruments in the Upper Canyon were deployed at water depths of around 2,000 meters. And then we had a gap of about 600 kilometers where unfortunately we weren't allowed to put any instruments. And then we had a second array of OBS instruments in the distal channel at water depths of 4,000 to 5,000 meters. The bottom right image shows how we deployed the OBSs on the canyon terraces, so outside of the flow path, so safely on the terraces. And often where we deployed OBS instruments, we had an ADCP in the channel next to it, so we could compare the OBS data and the ADCP data. So we had 3 research questions that I'll try to answer in this presentation and that we had when we deployed these instruments. So the first question is, well, can we use OBSs to record turbidity currents? And if we can, what is the seismic signature of these flows? And then going into a little bit more detail, we wanted to know what the OBS data could tell us about the internal structure of turbidity currents. And finally, how does the turbidity current flow behaviour in the Congo Canyon compare to current models of how turbidity currents behave? So to look at the turbidity currents recorded by the OBSs, we looked at the data in both the time series and the frequency domain, and that's shown in these 2 figures on the right. So on the top right, we have a seismogram, which shows a time series of ground motion recorded by the OBS and generated by the turbidity currents. Below that, we have a spectrogram, and this is a plot of the signal frequency against time with the relative intensities of the frequency components shown as heat. So high intensity is the yellows and the whites. So these methods kind of answer our first research question, which was what is the seismic signature of turbidity currents? We can see in both the figures that the events have fairly sudden onsets. This turbidity current contained 2 pulses. In the frequency domain, the signal was concentrated below 10 Hertz, and the signal lasted for between 0.5 and 14 hours for all the events that we recorded. One other method to tell you about here is that we determine the transit velocities of the turbidity currents between the OBSs by noting the arrival time at each OBS and then the distance between subsequent OBS stations. So these figures on the right show you a summary of all the events we recorded by our OBS instruments during the 8-month deployment period. So top right shows the runout distance of the turbidity currents based on the seismic station that they were recorded to reach. And the table below shows the transit velocities of these events with the faster flows shown by the red and orange colours. So you can see that we recorded a variety of turbidity current runout distances. Some of our flows were confined to the Upper Canyon, so had runout distances of less than 200 kilometres from the shore, whereas we have 3 turbidity current pulses that traverse the whole array, and I'll discuss those in a bit more detail in the subsequent slides. Just briefly on the left, this is a spectrogram of what a small turbidity current looks like. So you can see that the signal is fairly short duration, it's just about an hour. And for these flows, the flow velocities were typically less than 5 meters per second. And I put this on here just so you can then compare how this flow looks like compared to some of our bigger flows. So this is the seismic signal of our biggest event that we recorded in the data set. So this is the canyon flushing flow from the 14th to 16th of January 2020. And we knew to go and look for this flow because this was the one that broke all our ADCP moorings and had them floating on the surface of the ocean. So it was kind of the first place we went to look for an event. And on the right, we have the spectrograms of the events moving through the system. So the top four panels show the signature of a turbidity current moving through the upper canyon or Angolan waters in this figure. And then we have a gap of 600 kilometers. And then you can see the turbidity current moving through international waters or the distal channel. And one thing to say about this event is that it contained pulses. So we hadn't realized that from the ADCP data because the ADCP data just told us the arrival times of the events and then the moorings broke. Whereas with the OBS data, we had the fantastic opportunity to see the whole flow and kind of get an idea of the internal structure. So we're really interested to see that this event appears to be pulsed. And we have two pulses, pulse 1 and pulse 2 in the upper canyon. And then these are kind of amalgamate to make one pulse in the channel. And then 40 hours later, we had a third pulse, which traversed through the whole of the system. On the top left is a plot of the transit speeds of the turbidity current pulses with distance from the source. So you can see that the flows accelerated in the canyon array and then reached maximum velocities by the time they reached the distal array, about 800 kilometers offshore. And then we can see that the flows kind of keep a very similar velocity and maybe decelerate slightly as they move a further 300 kilometers offshore from 800 to 1,100 kilometers. The bottom left figure shows the pulse duration. This is really interesting as well. You can see to start with that the pulse duration was a lot longer than our smaller flows, which I showed in the earlier slides. So our smaller flows had pulse durations of around an hour. Whereas this turbidity current had some really long pulses. In the upper canyon, the pulse length was around 6 hours. And then the pulse 1 in the channel, the pulse length had increased to around 14 hours. So really long pulses of seismic energy, which was great for us because it meant the flows were really easy to find in the data set. I just wanted to very briefly show you our other canyon flushing turbidity current that we recorded in the seismic data, just because it has a slightly different signature. Again, you've got the spectrograms of the turbidity current moving through the system on the left and right panels, and then the transit speed and the pulse duration. So this flow had a pulse duration of around 3 to 4 hours and didn't really seem to change too much. And the flow traveled at a slightly slower speed, getting to a maximum of just below 6 meters per second in the channel, and then slowly decelerating ever so slightly from 8,000 to 1,100 kilometers. So on to the discussion and trying to answer those other research questions we said at the start. So we wanted to know what the OBS data could tell us about the internal structure of turbidity currents. And for this, we were able to compare the seismic data with the ADCP data we had from the flows that we captured before all the moorings broke in January. So these were just for the smaller flows, but you can see this on the panel on the right-hand side. So the top panel is the data from the ADCPs. So this is the velocity profile in the water column showing a turbidity current event. And then on the same time series below, you can see the seismic signal captured by the OBS that was adjacent to that ADCP. And you can see instantly that the seismic signals are only generated at the flow front. And in fact, we found that the seismic signals were only generated at flow speeds of greater than 1 meter per second. And based on previous work, we've interpreted that the kind of what we're calling the seismically noisy part of the flow is produced by a fast-moving, high-concentration, dense frontal cell. And we've got a few lines of evidence for this. Previous work has inverted ADCP data to get concentration and has shown that the front of the flow contains a higher concentration or a coarser grain size. Also, often when we had our flows recorded by the ADCPs, the moorings were moved slightly, suggesting that there was a very dense part of the flow able to tilt the moorings. And finally, we compared our seismic signature with the seismic signature of other terrestrial geomorphic processes such as debris flows and snow avalanches, and they showed fairly similar signatures. And then also to note that the dilute trailing body and tail fail to generate a seismic signal. So it really seems to be only the very front of the flow that we're capturing with our seismic data. And what's really exciting is that we can take this understanding about the internal structure of the smaller flows, but apply it to these big canyon flushing flows, which we haven't really been able to look at before. I'm going to focus now on the 14th to 16th January 2020 event. And we can see it contains this seismically noisy, fast-moving section for really quite a long time, lasting up to 14 hours. And we've been able to convert this to the distance that that pulse length must have been to record a signal in the OBS as it came past, based on the length of the signal, the transit velocities of the flow, and the fact that we're quite confident the OBSs can't really hear the flows more than 5 kilometers away. So I've shown the distances or the lengths of the pulse that we've estimated on top of the spectrogram images. So you can see that the pulse one length in the upper canyon was around 80 kilometers long. This was when the flow was accelerating. And then in the distal channel, the pulse length was closer to up to 390 kilometers long. So it really was an incredibly long, dense part of the flow going past the OBS.
2 minutes.
Okay, perfect, thank you. Very briefly then, to say that we also have an idea about how long that trailing body and tail of the flow might be based on the temperature data for the most distal OBS, and that's shown in the bottom left here. What we can see is that we have an rapid increase in temperature that really well matches up with the arrival time of the turbidity current at this OBS. And then we see a continued increase in temperature at the OBS for a further 21 days before seeing quite a rapid drop off in temperature again. And we've interpreted this as to represent that the turbidity current is still providing warmer water for those 21 days, so that maybe the turbidity current lasted around 3 weeks. And then our final research question, how does the turbidity current flow behaviour compare to current models? What's really interesting, and Pete's already alluded to this, is that the seismically noisy head of all 3 pulses that we recorded going through the system for the canyon flushing flows appeared to reach a near equilibrium state, both in terms of the pulse duration and also the flow velocity staying relatively sort of similar and only decelerating slightly from 800 to 1,100 kilometers. So this suggests that the dense, seismically noisy part of the flow is not actually stretching, despite eroding huge volumes of sediment, which Sean will present more of in the next talk. So this suggests that the front of the flow is traveling as a kind of dense traveling wave model, which was suggested by Harima et al. 2020, which suggests that the head maintains a similar velocity and duration and then sheds material into the body of the flow. And this is the first time we've really seen this for such a large canyon flushing flow. It's also interesting to note that this is one of the first examples of a pulse turbidity current not generated by earthquakes directly monitored. So we see this pulse turbidity current behaviour. So then to conclude, we've shown that turbidity currents produce distinctive seismic signals, and we've provided a new method to monitor turbidity currents in the natural environment. We've calibrated the seismic data with the ADCP data, which suggests that the fast, high concentration front of the flow produces the seismic signal. The canyon flushing turbidity currents contain remarkably prolonged seismic pulses, around 14 hours long and around up to possibly 390 kilometers in length. And these pulses seem to reach a near equilibrium state, despite the fact that they are continually eroding large volumes of sediment. So I'll stop there. Thank you very much.
Fascinating, Meg. Thank you very much for that presentation. So I can ask something that really interests me, because I see no questions in the question, which is, so what is actually the source mechanism, so the processes for the seismic signal that you are measuring?
Yeah, that's such a good question, and I'm glad you asked, because I didn't really have time to explain, because to be honest, we're not too sure yet. It's quite tricky to sort of match up what is generating the seismic signal to what we see based on the data we have so far. So in terrestrial studies, they've kind of only just started to be able to confidently work out what is generating the seismic signals in, say, debris flows and rivers, whether it's water turbulence or bed load. But we are quite confident that the process producing the seismic signal is part of a dense flow, But whether it is grains kind of hitting the bed and producing the seismic noise, or whether it's kind of like the erosion process producing the seismic noise, we're not really sure. I think that's something for the future.
Fascinating. Well, we'll keep track of it. Thank you very much.